Welcome to this explainer. Today, we're taking what's usually a pretty dry textbook chapter on geometric proofs and transforming it into a visual guide on mathematical shape-shifting. We're talking about area theorems, and specifically, the rules that govern how shapes can morph and slide around on a 2D plane without losing a single fraction of their overall size.
So, think about this for a second. Can a shape completely change its form, look absolutely entirely different, but keep the exact same mathematical footprint? Well, it turns out geometry actually lets shapes morph dramatically while keeping their underlying properties 100% intact. By the end of this explainer, you're going to have a complete shape-shifting toolkit.
All right, let's kick things off with Section 1, Equal Areas versus Congruence, defining the boundaries.
Before we literally start sliding shapes around, we need to set the ground rules on how we actually measure them. A massive misconception here is that shapes have to look identical to be equal. They really don't. Equal figures just mean they take up the exact same amount of 2D space. Their area is the same. Congruent figures, though, that's your strict photocopy. Identical shape, identical size. So all congruent shapes have equal areas for sure, but equal areas absolutely do not mean the shapes are congruent. They can look wildly different, as we're about to see.
Moving on to Section 2, the parallel universe, setting the tracks.
To really master this shape-shifting, we need to understand the environment where it actually happens. Take a look at this. Imagine these dotted horizontal lines at the top and bottom as a literal set of railway tracks that the corners, or vertices, of our shapes can slide along. We've got a parallelogram, a rectangle, and a triangle here, and they are all trapped right between these exact same straight tracks.
Now, when figures are drawn so their bases sit securely on one straight line and all their top vertices touch another line that's strictly parallel to the first, we say they are between the same parallels. And why does that matter? Well, because whenever figures are locked between these tracks, it's a mathematical guarantee that they all share the exact same altitude or height. It literally doesn't matter how far to the left or right they lean. Their vertical height is completely locked in.
Okay, let's look at Section 3, the parallelogram rule. Theorem 19.
Now that we have our tracks firmly laid down, let's check out the very first major law of physics in our 2D world. This right here is Theorem 19. It tells us that parallelograms on the same base and between the same parallels are equal in area. Honestly, this is the granddaddy rule. It's the core building block for almost everything else we're going to uncover today.
It is so cool seeing this in action. Look at the original parallelogram here, the one labeled ABCD, leaning just a little to the right. Now check out ABF, leaning way further to the right. You'll notice they both share the exact same base at the bottom, line AB. And their top corners? They just slide along that same upper parallel track. So Theorem 19 is basically telling us that shape ABCD essentially just sheared over into ABEF without losing a single drop of total area. Of course, in geometry, we don't just take things on faith, right? But instead of getting totally bogged down in dense textbook jargon, let's prove this in 3 incredibly satisfying logical steps. First up, look at the outer triangles created by this shift, triangle ADF on the left and BCE on the right. Because of angle-side-angle rules, they're completely congruent. They're identical. Step 2 is where the magic happens. See that huge shared middle chunk, area ABCF? If you take that shared middle block and stick the left triangle onto it, boom, you get your first parallelogram. Slap the right triangle onto it instead, you get the second parallelogram. Since the triangles are identical and that middle piece is shared, the total area of ABCD perfectly matches ABFE. It's really that simple.
Which brings us to Section 4, the triangle connection, cutting things in half. So, let's see how this applies to our next family of shapes. Theorem 20 takes the exact logic we just used and applies it to triangles. It states that the area of a triangle is exactly half that of a parallelogram on the same base and between the same parallels. Meaning, if you can spot the parent parallelogram, you immediately, without doing any crazy math, know the area of the child triangle.
And comparing these concepts side by side makes the natural progression really clear. If you just slice a diagonal line right through a parallelogram, it perfectly splits the shape into 2 identical triangles. So naturally, one of those triangles is exactly half the total area. It's a gorgeous visual proof. No numbers needed, just pure structural understanding.
Which naturally leads us straight to Theorem 21. Think about it. If all parallelograms on the same base and tracks are equal, and a triangle is half of that parallelogram, then logically, any triangle sharing the same base and the same parallel tracks must also have equal areas to each other. You could slide the top point of a triangle literally anywhere along that upper parallel line. The shape is going to warp, it'll stretch, it'll skew, but its area, that stays completely frozen in place.
All right, section 5, the magic of medians, splitting the space.
Now we're going to take these parallel tracking rules and apply them straight inside the triangle itself. Let's ask a deceptively simple question. What happens if we just draw a line straight from the top tip of a triangle, right down to the exact midpoint of its base? It sounds like an everyday geometry homework problem, but the implications for the area are actually mind-blowing.
As you can see beautifully mapped out here, drawing that median line, line AD, chops the primary triangle ABC into two smaller, distinct triangles. But here's the secret sauce. Those two new triangles, they have strictly equal area.
But why does that happen? Well, look closely at the structure. Step 1. Because line AD hits the exact midpoint, we know the bottom base of the left triangle is exactly equal to the bottom base of the right triangle. Step 2. Notice they both share the exact same peak vertex at the top, point A. So, because they sit on equal bases and stretch up to the exact same peak, they are mathematically trapped in the exact same altitude. Same base, same height. Therefore, their areas just have to match perfectly. Splitting the base in half splits the area in half, period.
Let's bring it all home in section 6, master the shapeshifter, putting it all together.
Finally, let's talk about why building this exact geometric toolkit is so incredibly useful for real-world mathematical applications. At first glance, this higher-order thinking skills diagram looks like absolute chaos, right? It's a terrifying jumble of overlapping triangles, intersecting diagonals, and parallel indicators just flying everywhere. If you tried to calculate the area of these shapes using just raw numbers in a ruler, you would literally be here all day. But here's the thing, you don't need numbers. Once you train your eyes to see the shape-shifting tracks, the parallel lines, the shared bases, the medians, the chaos instantly evaporates. You can look at a crazy complex web of lines and immediately know which overlapping zones are identical in size simply by tracing their tracks. It transforms a frustrating math problem into a really satisfying visual puzzle. And it leaves us with this thought. Armed with just a few fundamental rules about boundaries and frameworks, what other impossibly complex problems in the world are just waiting for you to calmly slide the pieces into place and reveal the hidden order inside? Thanks for checking out this explainer, and keep exploring those parallel tracks.